Alright, today's section is 4.2, Newton's first law. The three objectives are going to be to explain the correlation between the motion of and the net external force on an object, to determine the net external force on an object, and to analyze problems when forces are balanced in a state of equilibrium. First, let's take a look at Newton's first law, which states that an object at rest will remain at rest, and an object in motion continues in motion at a constant velocity unless acted upon by an outside force. So if an object is sitting here in the middle of space with no forces acting on it, no weight, no gravity, no friction, nothing, no applied force, it will remain at rest. But if the object is currently moving at some velocity, it'll keep moving at that velocity. So if I just simply tap an object in space, it will move at that velocity forever, because nothing else is going to act on it to stop it unless it, gets caught into a gravitational field from a planet. So an object moving will stay moving, but an object at rest will stay at rest. This is also called the law of inertia. The net external force, also known as the resultant force, is simply the sum of the forces acting on an object in a given direction. So remember that an object acting, or a force acting at an angle like this, on an object, would have components. So let's say the object is here. This force would not only be acting at that angle, but it would really have like an Fpy and an Fpx. So we'll talk about how to break it up into components and see how we're going to work with that as well, the same way we worked with our initial velocities. Again, though, the idea is that we sum all the forces acting in a given direction. Let's take a look at an example of that now. Number 1 says a crate is pulled to the right with a force of 82 newtons. Here's our crate pulled to the right. And to the left with 115 newtons, up with 565, and down with a force of 236. So imagine this object is in the middle of space. Clearly it's not on a table, it's being pulled in every direction. So, or we could say it's a bird's eye view, whichever way you'd like to say. It's being pulled in all the directions. But the idea is that we have 4 different forces. We can label them with, FP1, FP2, FP3, FP4 for a force of pull 1 through 4. We could also label them with directional, so we could say that this is like F1x, this is F2x, this is F1y, this is F2y. Now, if we're going to be looking at the net force in each direction, we have to analyze each direction. So we have to take a look at the net force in the x direction first. And that's going to be equal to F1x, because that's to the right, minus F2x, because that is acting to the left. And in the y direction, we're going to have F net in the y. In this case, acting up happens to be F1y, and acting down happens to be F2y. So the subscripts are similar to the x direction. But the idea is that the problem will change, so you have to write this every single time. We can't just remember these rules at all. Well, if we go ahead and plug in values now, F1x minus F2x is going to be 82 minus 115, both newtons, which yields negative 33 newtons, again in the x. In the y direction, though, we're going to notice here that we've got 565 newtons minus 236 newtons, giving us a total force in the y direction of 329 newtons. So our total force in the x is negative 33, and our total force in the y is 329. That means that the object is going to move to the left in the x because of this negative sign here. It's got to move to the left because the overall force, this force, was bigger than this one, so the overall force will be the left. But in the y direction, this was bigger than this, so we ended up with a positive number, so the overall force is up. So the overall force is to the left and up. So if we're looking at this, the force is to the left, and then it's up. Well, how much to the left is it? Well, it's to the left by a value of 33 newtons, so let's put 33 there. And we could say that it's acting up with a value of 329. Now, for this problem, we're technically done when we get to this part, but let's take a look at something else now. Let's talk about resolving these two components into its resultant vector. If it's moving to the left and up, technically the force is really acting upward at an angle. And it's going to be at a pretty steep angle. Okay, we should really complete this triangle. This is called the resultant vector. And this is the overall force acting on the object when we resolve the two components into one directional or one vector component. Now, what we're going to see is we're going to have Pythagorean theorem that exists here. 33 squared plus 329 squared equals r squared. And that'll give us an r value of approximately 330.7 newtons. It's really quite interesting to point out the fact that this number doesn't go up very much. This value of 330 is not much higher than the y component of the overall force of 329, simply because this has very little significance. Squaring 33 is like around 900, but squaring this number is going to be around 90,000, okay, if not more, over 100,000. So this has a much higher significance. So when you add this square to this square, this one has like no effect almost. So this answer is very close, only 1.7 newtons greater. Okay, so that is the value of our resultant vector. Now you might also wonder, well, how much of an angle does this act at? Because it's clearly acting at an angle. Well, there's theta. So let's write our ratio to solve for theta. We can see that we have tangent because we've got opposite over adjacent. So tangent of theta equals 329 over 33. Therefore, theta is the tangent inverse of 329 over 33. Making sure your calculator is in degree mode to give us an answer in degrees, theta turns out to be an angle of 84.3 degrees. And that makes sense. It must be closer to the y. Remember, 45 degrees means that it's split evenly between x and y. Less than 45 means it's more in the x. More than 45 means it's more in the y. It's definitely more than the y, more in the y direction because of this value. It's much greater than 33. So let's write a solution. Our solution says that the overall force is 330.7 newtons at an angle of 84.3 degrees northwest. Again, where does the northwest come from? Take a look here at the diagram. This is west, right? Then we're moving north. So technically this is west and this is north of west. Our vector is 84.3 degrees north of west. North of west. Next, we need to define a term called mass. And many of you have heard of mass before, but we need to make sure we really understand what it is. And the interesting part is to realize that it's a measurement of the inertia of an object. The inertia of an object, or as we've heard many times, the amount of matter that makes up an object. That's the standard general definition. But the one we want to really look at is this definition. The measurement of inertia. Now before we even get to that, let's make sure we clear something up. Weight and mass are different. The weight of an object is the force the object feels due to gravity. Remember, it's the force due to gravity. And this changes based on where you are. If I'm on Jupiter, it's a different number. If I'm on a higher altitude, it's a different number. So weight is a function of the location. So if it's at a different height, a different planet, a different solar system, whatever it is, completely, the weight changes based on the gravitational force because of the gravitational field and the acceleration that is felt. But the mass of an object will never change. The amount of matter that it makes up doesn't change based on planets. Granted, you could lose mass based on, exercising and losing material and, sweating it out. But technically, if I go from here to the moon instantaneously, my mass is the same. But my weight definitely changes. My weight on the moon is about 1/6 of the weight on Earth. Let's talk about the measurement of inertia now. What we really want to do is to think about an example where we have, imagine a golf ball and a baseball. Here's the golf ball, here's the baseball. If I were to hit them with the same force, clearly the golf ball moves a lot further and easier. It's not easy to move a golf ball than it is to move a baseball, hitting them with the same force. Well, that's because, a lot of people say this has less mass, right? You would say the mass of this object is less than the mass of this object, so it's easier for it to get moved, which is true. But remember the definition of inertia. Inertia is an object's tendency to remain at rest, or an object in motion to remain at motion. Well, both of these objects are at rest. Clearly, this one wants to remain at rest more than this one does, because it moves further. So this one's inertia, its tendency to want to remain at rest, is less than this one's inertia. So this object here, the golf ball, it's like, you know what, he hit me as a golf ball, I'll go pretty far, but a baseball wants to remain at rest. Make a more extreme example, think about like a kettlebell, the ones that the Olympic weight trainers use. You hit this with the same force you hit a golf ball with, it probably won't move at all, because its mass is the greatest of all, or its measurement of inertia is the greatest of all. It really wants to remain at rest. You hit it, it's not going to really move at all. So mass is really a measurement of inertia, or a measurement of an object's tendency to remain at rest if it currently is at rest. Now let's take a look at an application of inertia. A very basic one, which is pretty amazing to think about. Simply using inertia, seatbelts. So seatbelts use the laws of inertia. Now, what happens is this. The car comes to a brake, and whenever a car brakes, you'll know that the objects, or the person is going to move forward, which is what the seatbelt prevents you from doing. All objects want to move forward if the car brakes because of inertia. Again, an object in motion wants to remain in motion, so this object wants to continue to remain in motion, but the seatbelt's going to hold it back. But this mass, there's nothing holding it back. So this mass will slide forward. When this mass slides forward, this pin connection here will also move, causing this rod to pivot. Okay? It'll pivot on this pivot point, and it'll create an angle. And when it pivots, really, what it's doing is it's changing this location, and it's engaging with this ratchet right here, with this gear. And it engages with the ratchet. And when then the seatbelt goes to pull for the object or the person to move forward, the seatbelt wants to pull. So it wants to pull up, which will cause the ratchet to move in this direction. But because this rod is here, it's going to prevent this ratchet from moving. So this little block here sliding forward, turning this rod, engaging the ratchet, is what causes the seatbelt to lock in place. And so you'll remember, if you want to disengage the lock, you need to give a little bit on the seatbelt. And when you give a little bit on the seatbelt, meaning you pull it this way, it causes the ratchet to turn back in this direction now. And when the ratchet turns in this direction, the rod disengages, and then it opens up, or it allows it to move freely. Let's finally take a look at a term called equilibrium and start by simply defining it. So equilibrium, the state in which the net force on an object is zero, or there is no change in the body's motion. So a body at rest is clearly in equilibrium. We can all see that. Its motion is not being changed. It's at rest. It's still at rest. Now this is interesting though. A body that's moving with a constant velocity is also at equilibrium because its motion is not changing. Sure, its position is changing, but its motion is not changing at all. It's moving consistently throughout. So we have to talk about this. If there is a net force of zero on an object, that means there's no acceleration. So we can write down, yeah, the net force is zero, but acceleration is also zero. And if acceleration is zero, well, that means that velocity is either zero or the velocity is just constant, which comes back to reiterate what we said a moment ago. There's no change in the body's motion. So these are the three key facts we want to write down for equilibrium that always hold true. From this section is from page 135, numbers 1 through 3.